Okay, good morning. Welcome back to ECE484, fall 2021. Sorry I was late putting up the link, the YouTube link. Hopefully people can join. I'll be sure to put up the remaining lectures for the week after class. Okay, so what have we been talking about? We've been talking about nonlinear systems. We're scraping the surface on a big topic. And what we've been talking about is essentially approximating nonlinear systems using linear ones, a very common technique throughout engineering and physics, and designing controllers then for the linearized system. Okay, and so last class we did some examples of taking a nonlinear state space model and then linearizing it at some equilibrium. Okay, and this week's problem set asks you to do that a bunch of different times for different examples of systems. We talked about this notion of, okay, after you do your linearization, the output of that procedure is a linear system in state space form. So you get this four tuple of matrices, A, B, C, D. And all of our control design techniques up till now have used a transfer function model of the plant, not state space models. And so the last step after you do your linearization is to then generate a transfer function model. And so we derived this state space to transfer function kind of function. That's what it's called in MATLAB. And basically the idea is that the four tuple A, B, C, D generates this transfer function. So here's our transfer function. Okay, so it's a formula. You plug in the matrices A, B, C, D into the formula and you do the calculation and you will get a transfer function. Okay, I will comment that when you go from state space to transfer function, it's always unique. You get a unique transfer function for a given state space model. If you go from a transfer function, so an input-output model, to a state space model, it's never unique. And we'll see this later on in chapter 6. Okay. And then the last thing we did, okay, why were we doing all this linearization? At the end of the day, it was to then design controllers. And so we were doing control design via linearization. And that's where we left off. And I was in the middle of an example when we stopped. And so I'm going to remind you about that example and then continue. Okay, so we were looking at this mass spring damper system where we had this softening spring. So the force exerted by the spring gets weaker the more you stretch it out. Okay, it's a nonlinear force. But here's the expression for the nonlinear force. Okay, and what we wanted to do was to design a controller to keep the cart located at Q equal to 0.5, so say half a meter away from the wall. And then we wanted to do step tracking. So basically the idea would be that you keep the cart at 0.5 and then you command it to move, either left or right from 0.5, and you want it to track that command perfectly in the limit, in steady state. Okay, so we did our full procedure. So I'm not going to go over everything again, but we did our full procedure. We found a state space model. We linearized by first finding equilibrium configuration. Then we got the matrices A, B, C, D. And finally, we got the transfer function. So I'll remind you that in our linearized model, delta U was the difference between the actual force being applied to the mass minus the force required to keep it at 0.5, right, to balance out the spring force. And the delta Y is sort of the measure of how far the output, which in this case was the position, how far the output is from its value at equilibrium. And so delta Y measures how far the actual position of the mass is from the place where we did our linearization. All right. Then we define these symbols, capital delta Y and capital delta U, to be the Laplace transforms of these quantities. And we've got the transfer function. Okay, in this case we plugged it into our formula we just discussed, and we ended up with this expression here. And that's where we left off. Okay? So now, like I said, in this example, what we're going to do is we're going to take this model, we're going to design a simple controller. The design here is very simplistic. We're going to do a very simple design. And then the thing I want you to focus on is, at the end, the way we test/implement our controller, right? There's a bit of a subtlety there. All right? So let's continue. Okay, so there's our transfer function model. And now suppose that you go to the lab and you then run some experiments. Maybe you take a step response of this system near the equilibrium configuration. And then you do your system identification. Okay, I'm going to assume that we've done that to get some numerical values to actually be able to design our controller. Okay, so for the purposes of this example, let's suppose we've done some system identification. To get, I'll just use some simple numbers, m equal to 1, b equal to 1, k equal to 1, and a squared equal to 1/3. All right, and then I'm just going to plug those numbers in to get our kind of model of our plant. And so we'll get P of S Okay, that's just what you get when you plug in the numbers. Now, I'll remind you that our specs are to keep the plant at this point 0.5 and then step tracking. Now, the plant has poles at s equal to -1/2 plus or minus j 1/√2. Okay, so the plant is open loop stable, right? I don't need feedback to stabilize this plant, right? In other words, if I just apply this constant u bar, this force, this mass will eventually settle down at the desired location, 0.5. So it's not like the pendulum example last class where it was open loop unstable. This case is open loop stable. However, the spec was step tracking, so we still want to be able to accomplish that. And again, we notice that the plant does not have a pole at the origin, so we need to design a controller to do that. Okay, if the specification was just stability, we don't need to do anything. The plant is already stable. But in this case, we want step tracking. So let's try a simple controller, try a PI controller. So given the specs, let's try a PI controller. Now remember, the purpose of this example isn't so much the design. I'm just going to pick a simple controller. The purpose of this example is to see how we would then implement this on the nonlinear system. Okay, so basically the control design problem, once I've decided to use a PI controller, is to pick KP and KI. Now again, I know that I'm going to get tracking as long as I get stability. So I just need to pick KP and KI to get stability because there are no other transient specifications. Okay, so in this case, we can use our simple tools. So using our linear tools. So two tools you could use here to pick values for KP, KI could be something like Routh-Hurwitz. Root locus. We can pick values of the proportional gain and the integral gain. Okay. Again, this is not the main point of this example, but let's just do this in this case using root locus. Okay, so if I were to draw the root locus, what do I do? In the S-plane, I will draw the poles and zeros of the plant in the controller. Poles will be x's, zeros will be circles. So the plant, we said, had poles at -1/2 plus or minus j times 1/√2. Our controller, well, let's rewrite our controller. Let's write our controller in the following way. Okay, so I put it over the common denominator, and then I'm just going to define this quantity by factoring out the Kp. I get my PI controller written this way. So the PI controller design, you can think of it as picking where you want the 0 of the controller, and then finding a value of Kp, and then of course you can back calculate to get the integral gain if you want. So in this case, we just want to pick the 0. Now, again, this is just a simple, quick design. What we don't want, is these poles. So now, okay, so now we've got the pole at the origin coming from the controller, and we need to pick a 0 location. And what we don't want when we pick our 0 location is that we would like these poles to not go into the unstable region, okay? And if you recall, we know that they're going to go off to infinity along asymptotes. So we just want to make sure that these asymptotes stay in the left half plane, okay? And so in this case, the centroid of this root locus is going to be the sum of the zeros minus, sum of the poles, sorry, minus the sum of the zeros. So in this case, the poles, add up all the poles, and you get -1. The 0, we haven't decided yet, so let's say let's put that there. We haven't picked a value of z. Divided by the difference between the number of poles and the number of zeros. In this case, 3 poles, 1 0. So 3 minus 1. Do the calculation, you get z minus 1 over 2. Okay. So this centroid is going to be somewhere there, and our poles are going to go off to infinity along this centroid, along this asymptote. And so we want this centroid to be in the left half plane so that when we start increasing the value of Kp, the poles don't slip over to the right. Okay? And so this suggests that to keep the centroid in the left half plane, we should constrain our 0 to be between 0 and 1. Okay? So that we get a negative value for the centroid. Okay? And so I'll draw the picture where we've picked the pole, or the 0, to be exactly at -1/2. So if we do that, then our root locus will look like this. This guy's going to come that way, and these guys will go off that way. Okay? It's not the best controller. Again, the point of this example is not the control design. The point of this example, we'll see in a moment, is implementing it on a nonlinear system. Okay, so I'll pick Kp equal to 1, Ki equal to 0.5. And you can see from the root locus that our settling time is not going to be very good, right? We're going to have a pole somewhere in this region. Not only that, we're probably going to get a lot of overshoot because we're going to have 2 poles kind of going off to infinity, kind of the imaginary part getting bigger and bigger. Okay, so not the best controller. I'm not saying this is a great controller, but let's suppose that we're happy with it. Doesn't look like a great controller. In terms of settling time, percentage overshoot. But let's just say we're happy for the purpose of the example. Okay. Again, there were no transient specifications, so the only specification was stability. Okay, so now we want to check whether or not we're satisfied with the controller, whether it works. Now remember, we designed the controller for the linearized plant, i.e. we approximated the nonlinear mass spring with a linear model and designed our controller. So what we do is we want to test whether it's going to work. And remember, one of the things is that this linearization is not going to be a very good model if we go too far from the equilibrium configuration. And in particular, if you apply too big a control signal, you might get far away from that equilibrium configuration. Okay, so we need to test whether or not it's going to work, not on the linear plant. We know it's going to work on the linear plant in terms of the specs. We need to test on the nonlinear plant. Okay, so let's draw a picture of that. to implement C of S, we discretize, of course. Right? In this course, we're implementing our controllers on computers. So you discretize it. You make a choice of a discretization method that we talked about before. And then we simulate. /test using the nonlinear system. Okay, so let's draw a picture of what the block diagram would look like when you do your testing in your simulation. Okay, so it's going to be the following. So bear with me while I draw this. So over here, I don't like that. Over here, we'll have our nonlinear plant. So let's say sorry. Okay, so this is our mass with the softening spring. It's the plant. Right? You can't change the physics of the system. Even though we designed for the linear system, the real system is nonlinear. Okay, it has input U. Output Y. Okay, and of course we're going to implement everything on over here is going to be what's in our controller. So there's H. Okay, so here we're going to have our sampler, ideal hold, and so this will be the interface to our plant. Okay, all right, so that's the part we can't change. That's the thing we're trying to control. What we're going to do is over here we'll have our controller. So we'll have d of z over here. But now here's where the little subtlety comes in. Our controller does not produce the signal U. Remember that we were working with the linearized model. What the controller produces is delta U, the difference between the control signal at equilibrium and the actual control signal U. So what we need to do is we need to bias what's coming out of this block to get U. And so what we want to do is we want to add U bar. Remember that delta U is equal to U minus U bar, and so you just rearrange that equation, and so essentially you're biasing your controller. And this is done offline, right? Offline, you compute the value of U bar using your model, and then you store this value of U bar on the computer, and you bias it, right? You add the bias to whatever comes out of your linear controller. Right? This is the subtlety. We have to do a similar sort of thing at the output, right? The controller is not controlling Y, the linear controller, it's controlling the deviation from the value of Y at the equilibrium. So what we'll do is we want to take the actual output Y and generate delta Y from it. And so we're going to have to subtract that value. Oops, I think I've got these backwards, sample and hold. Sorry. So the idea here is you measure Y from your sensor and you subtract the pre-computed value Y bar, right? This is where you did your linearization at. And what comes out of that is delta Y. And now you're in business. Now you're basically delta U and delta Y are the quantities we were doing our linearization or our control design with respect to. And so The rest of the diagram is the same. Okay. And so what about the reference? What does the reference look like here? Right? The reference is usually what we call this signal here. Now the reference, when you're dealing with linearization, is not a reference for the output y. It's a reference for the output, it's for the output delta y. So you're commanding desired values of delta y. So I'm going to write that as delta r to make that very clear. Okay? So when you go to test, do not forget these bias terms. Okay? Very important. The system won't work well. It won't work if you don't include them. And of course, the assumption when you go to simulate is that the plant, at least initially, is somewhat close to the equilibrium configuration when you kind of turn on the automatic controller. Okay? So to make this kind of even more explicit, let's draw like a picture of what we would expect to happen for this system. So for example, if we made the following command. So suppose that delta r is sort of jumps up to 0.25 for a few steps and then comes back down to 0. So delta r, say, 0, 1, 2, 4, 7. Okay, suppose that it jumps up to 0.25 for a few steps. And then back to 0. What does that mean physically for our mass? It means we're commanding it to, starting from the equilibrium value of the output, 0.5, we want it to move right 1/4 of a meter for 5 discrete time steps, and then go back to 0.5, the equilibrium value, for thereafter. Okay, so what are we commanding here? We want delta y to go to 0.25 for 5 sample periods. And delta y to go to 0 thereafter. Okay? And physically, like I said, i.e., y of t, which is equal to delta y, or is equal to q of t, sorry, which is the position of the robot, that should go to q bar plus 0.25 for 5t seconds, right? Whatever the sampling period is. Then y of t goes to q bar thereafter. Okay, so the subtle thing here, is keep in mind that after you've designed the controller for the linearization, you are commanding the deviation from equilibrium. Okay? And if you go too far from that equilibrium, if you command it too far, your linear approximation is not going to be very good anymore in general, and the controller might act unpredictably, right? You might get unpredictable behavior because your controller is based on a linearized model, and if you move too far away from the equilibrium, that model starts to break down. Okay, so control design using linearization, right? The key takeaway of that question, the most important thing, is the last step, right? When you go to implement and test, how do you interpret what you've designed physically? Okay, the last couple of things we're going to talk about in this chapter are things that, unfortunately you've probably done already in the lab, but we're going to talk about them anyway. and that is about inverting nonlinearities. I say unfortunately because, there's a lot of material to cover, and so decisions have to be made about when to cover them, and so this material might have been useful in lab 1, although it's in the lab manual anyway, but I wanted to go through emulation first before doing this material. Okay, so this is section 5.3. Inverting static nonlinearities. Right? So let's just think about the high-level idea here. So far, the strategy for dealing with nonlinear systems is to approximate them with a linear model. Okay? The concept in this section is a little bit different. It's not trying to approximate them using a linear model, but rather making clever choices of control, let's call them algorithms for lack of a better term, so that the system appears linear. Right? So it's kind of a clever choice of control as opposed to a modeling approximation, which is what we've done before. So before we get into it, what do I mean by a static nonlinearity? So a static nonlinearity is a nonlinear system with no dynamics. And what does that mean? That has no dynamics. i.e., the output at any moment in time of this nonlinear system only depends on the input at exactly that same time. It does not depend on previous values of the input. So i.e., the output at time t only depends on the input at time t, okay? Not previous values of the input. Okay? And let's do an example to kind of illustrate that idea. So I'm going to use kind of a notation throughout this section, and it's going to look like this. I'm going to have a system and I'm going to talk about these nonlinearities. I'm going to talk about them, I'm going to model them as this function phi. Okay? And so here we have u, I'll call the output v. Okay, so this is a system with input u, output v, and the symbol I'm using for the system is phi. And I'm going to look at 3 different nonlinear examples, 2 of which will be static, 1 of them will be non-static. Okay? So let's draw a picture. Okay, like I said, I'm going to do 3 of them, so let's copy this. Okay. So my first example will be one which we saw way back in chapter 1, quantization. Right, we said quantization was one of the sources of nonlinearity in an A to D and a D to A. And the graph of that quantization nonlinearity was this step. I didn't draw it very well, but something like that, okay? And the idea being that very small changes in the input are not reflected at the output because of finite precision of the A to D. Okay? Another example of a nonlinear system, so-called ideal relay, right? So when the input is 0, the output is 0, or less, the output is 0. And as soon as the input becomes positive, the output turns on, so it goes to 1. So the picture would be the following. Oops. something like that. So it's an ideal relay. So when U is small or less than 0, 0 or less, the output is 0. As soon as the output becomes positive, it turns on. It's like a logic element, right? And finally, relay with hysteresis. Okay. So it's kind of like the ideal relay, except that it has a bit of memory in it, right? So what'll happen is the output has to be sufficiently positive before it turns on. And stays on. But then when the input starts to go negative again, it doesn't turn off until it's sufficiently negative. Right? So the picture here is typically like this. Okay? So it has a bit of memory, right? So it delays the switching from on to off. It's sort of, you can think of it as a delay in the switching. Okay. Now, these are all nonlinear systems. However, notice that the first two have no memory. They essentially are, the output at any moment in time only depends on the input at that time. So all three systems are nonlinear. But only A and B are static nonlinearities. Okay. So the idea again is that the output of this nonlinear system only depends on the input at that particular time and not at previous times. Okay, so static nonlinearities pop up from time to time. We'll see some examples as we go on. And the idea in this section, remember conceptually we're doing something different than linearization, is that if we can get access to these static nonlinearities, in other words, if they show up in just the right way in our system model, we can account for them in our control design. So let's make that statement precise. So sometimes we can cancel the effect of a static nonlinearity through clever control schemes. All right? So we can hopefully, if we're clever about things, we can deal with these static nonlinearities through control design. Okay? And so the case we're going to consider is where the static nonlinearity shows up at the input of the plant or at the output of the plant. So I'll draw two pictures illustrating this. And then I'll explain what the pictures mean. So I said one at the input, one at the output. So the one at the input will be on the left, the one at the output will be on the right. Okay, so here we're going to have one of these static nonlinearities showing up at the input of the plant. Okay, something like this. Call this phi. And it shows up at the input. So actually I need to change my notation here. So the input is U, the thing coming out of that block is V, and so this should be V here. And then Y, right? So this is a plant, a dynamical model in state space form with one of these static nonlinearities at the input, okay? And then over on the left, on the right, sorry, we'll have the same sort of idea. Except that it's going to show up at the output. So okay, so here we have two systems, and what we're saying is this is a static nonlinearity at the input, and this one is a static nonlinearity at the output. Okay, of our plant, right? So the overall plant in both cases is that guy, and there's our plant there. Okay, so you have these two systems. One has a static nonlinearity at the input over here, and one has a static nonlinearity at the output. And basically what we want to do is, if we can choose the signal U coming into this block correctly to sort of cancel the effect of this guy, we can access the internal part of the plant, the dynamical part of the plant. Similarly, if we process the output that we're measuring smartly, we can cancel the effect of this nonlinearity and then work with just this block. Okay? And this is going to be particularly useful when these blocks here are otherwise linear systems. Okay, so canceling the static nonlinearity phi is especially useful when the rest of the plant is linear. In other words, instead of having those nonlinear state space models inside of the green boxes above, you have an otherwise linear system, right? Because then after you cancel the effect of phi, this static nonlinearity, you now have a linear system to work with. Okay, so let's do an example. It's similar to one in the notes, but not exactly the same. Okay, we want to design a controller for the plant. Okay, so notice that we have this nonlinear term showing up at the input, U cubed. So we want to design a controller for the plant to get step tracking. Okay, so let's take this plant and let's write it, or let's draw the block diagram for it as we did above. Let's draw it as a dynamical part with a static nonlinearity, either at the input or at the output. Okay, in this case, it's at the input, right? You see this nonlinearity showing up in the U term. Okay, so the picture we'll have in mind here is the following. Block diagram of plant. Okay, I'm going to draw it sort of as an instance of what we have above. Okay, and so the input is U, the output is Y. Let's call the intermediate signal V, just as we did above. And what do we have? Well, the nonlinearity here is phi of U equal to 1/3 U cubed. Right? That's coming from the right-hand side of the differential equation. And then what's left is an otherwise linear system. So it's like the picture above, but in a special case where what's left actually happens to be linear. Okay. So I guess you can kind of figure out what you should do here, right? We get to pick this signal u, right? That's our control input. And so the idea here is that let's cancel the effect of this guy by putting in a block here, which essentially does an inversion, cancels it out. And then, once we've added that block there, we'll have a linear system from this signal, ideally, to this signal over here. That's the basic idea. I mean, it's kind of very intuitive, right? It's what you would probably naturally want to do, but we're just trying to write it down a little bit more carefully. Okay, so to cancel the effect of the nonlinearity, consider the function phi(w) equal to the cube root of 6w. Right? So where is that coming from? It's basically trying to get rid of the effect of that phi term, that phi nonlinearity that's showing up at the front. Okay? And observe that when I compose these two functions, phi, right, so if I take the signal w, run it through that phi, or the psi, sorry, then through phi, the static nonlinearity, I get w back. Okay, and that's the kind of the idea I said before. We design our control signal w, run it through this kind of cancellation term phi, and then what we'll get is that v, the thing going into the linear part of the system, is equal to w. Okay, so this suggests the control architecture. Where again, we're going to just cancel out that other term. So let me again draw a block diagram. Okay. Okay, so let me start label some of these blocks. So this was the output y, the input u to our plant. The plant, remember, was this nonlinear term, phi, followed by this linear part. Plant. The controller, we said what we'll do is we'll try to cancel out that effect and design the signal w. So we'll call this the controller that will design C of S. And this block here will be the controller. Okay? And if we're good at modeling this phi term, then essentially what we would expect, hopefully, is that this term and this term cancel out, and now you have a linear system, right? You basically have a standard linear model, the kind that which we've been working with. So again, keep in mind the big picture here. The big difference here between this notion of getting a linear system, so notice at the end of the day we get a linear system, is that as opposed to approximating the model of a nonlinear plant, we're doing a clever choice of control to try to cancel out the nonlinearity and get a linear system. Okay? And so it's kind of a simple idea, but it's actually kind of an important idea as well in control design. So we can now design C of S for the LTI system (1 over S plus 1), and then implement the overall controller as above. Of course, you'd have to discretize and all that stuff, but you get the idea, right? That's the controller you want to implement on the computer. Okay? So for example, in this case, C of S equal to 1 over S works. Okay? Again, the point of this example is to sort of illustrate this notion of canceling nonlinearities at the input. Now, one thing about the implementation, of course, is that when we go to implement this, we're going to do it on a computer. So is that going to mess things up? This cancellation here is a continuous time cancellation. Are we going to be in trouble when we go to implement this on a computer? So the answer is no. And let's kind of see why. So remark. What does the implementation look like on a computer? Implementation on embedded system. Okay, and I'm going to zoom in particular on the part, the cancellation. So here's the part that I'm going to be interested in. What's happening at the interface, right? U is what's coming out of our controller, and so that's going to be coming out of a hold block. So what does that look like? Well, we're going to have the following picture. Okay, so there's our block, and then this was our cancellation. So it was the cube root of 6W. Okay, so this is the same picture as above, except I've added the hold and the fact that I'm implementing this on a computer. And so the question is, are we still going to get a cancellation? Well, despite the hold, despite the hold block, the cancellation still works. Still works, and we get that V of t equals W of k over the hold period. Okay? And this is precisely because it was a static nonlinearity, right? This nonlinearity, the 1/6 over u cubed, doesn't depend on previous values of the input. It's a static nonlinearity. And it's because of that that we get this equality over the sample period. So this is precisely because the nonlinearity that we're inverting is static. Okay, if it had been non-static, if it had some dynamics like that hysteresis, we'd have a problem. Okay. So that's a good place to stop. So again, what did we do today? Have a static nonlinearity at the input of a linear plant, make a clever choice to cancel it if possible, and now you have a linear system. And the conceptual difference is that we're trying to do an exact cancellation as opposed to an approximation. All right, I'll stick around if there's a question. Otherwise, I will see you tomorrow.